Awesomeness. Okay, so let's get going with the weighted residual method. Okay, so what we saw before was the following, that if I have some residual that I would like to solve in such a way that I find the minimum of the residual squared, I can write it in this weighted residual form, where I choose the form of this weighting function, the same as the form of this thing that I'm using here as an approximation in my residual. But what I have is essentially just multiplying the two to each other and integrating over the area, and then I have a scalar equation. That's what I have here. Okay, and then if I were to later on take the derivatives with respect to the coefficients that are in this weighting function, I can then recover the system of equation I need to solve for the other, for the A, B's, and C's, for instance, for those residuals unknown coefficients. And so I could have called this unknown coefficients of the residual function just, let's say, a capital C. And I could have called the variables associated with the weighting function, this D, E, and F, just capital W. And this is what I'm doing on the next slide. Okay, let's apply now the weighted residual method to the strong form. Here is the residual, three equations that I have. Spatial functions of x, y, and z. Capital C is essentially the coefficients with respect to which that sort of dictates now what's going on. And how do they dictate what's going on? Well, imagine these coefficients C define my displacement field. So they control, if I choose different C's, I manipulate my displacement field to be something different. I haven't talked about how they look or anything, but just conceptually, you can imagine. The same way it's with a quadratic function, I had A, B's, and C's. If I manipulate the A, B, and C, it changes sort of that displacement field to be. These C's also now, if I change them, would change the displacement field. And there's three displacement fields. One displacement field for X, one for Y, and one for Z. So typically the U, V, and W. And imagine these C's are now collectively controlling that. Okay. So choosing a different C, choose a different displacement field. That displacement field, in turn, if I take the gradients of that displacement field and then take the symmetrical part of the displacement gradient, I end up with a strain matrix. And if I multiply that strain matrix with the material that we're working with, I end up with a stress tensor. So this is what you can see here. The stress tensor is then controlled also by that same C's that sort of dictate the displacements. Okay. This is essentially just what we have here. So this sigma here is not something that's given to us. It's something we're going to guess now. We're going to figure out what sigma is the one that we need to, what this C's needs to be to best describe the equilibrium of this. So this is our residual equation. We would like to get this equal to 0, which is maybe wishful thinking, but we're going to try and do the best job we can. Okay. So take the residual that we have, which is now a 3×1 vector, and we dot it with a weighting function in such a way that we end up with a single scalar equation. So this weighting function is also three functions, one for the displacement in the U direction, one for the displacement in the V direction, and one for the displacement in the W direction. So this is what this weighting function means, okay? And the W are the coefficients that control the weighting functions. And if we were to take the derivatives with respect to these W's, I end up with a system of equations that allows me to solve for the C's. Same as what you did before. Okay, so let's see what we learn from this now, and how whether we can expand this and ask some critical questions. So if I expand this expression here and just substitute my expression for my residual in here explicitly, and then break up the two integrals, saying W dotted with this three equations for the divergence of the stress tensor, plus the W dotted with the vector of the body forces must be equal to 0 after I've integrated over the volume. This is what I have. Okay, so far the stress tensor is only worrying about, the only loading it's worrying about is body forces. At no point have we now linked in anything about the surface traction. So this problem at this stated here is not going to solve our strong form at the moment, because this stress tensor is completely unaware of the tractions that are being applied on the body. So we need to make sure we incorporate the tractions somehow into this problem. Otherwise, we're not solving the strong form. We are just solving for a stress field that somehow will satisfy for the body forces. So this is important that we just take a note about that. So the tractions are applied on parts of the surfaces of the body where we apply tractions. So what we know about how it's related to the stress tensor is that the stress tensor evaluated on that surface, dotted with a normal on that surface, is equal to the tractions there. And that must hold for all points where the tractions are applied. And also including where tractions are 0 that are applied. Okay, so all of that must hold everywhere. Okay. So that is essentially what we know. How do we bring this back into the game? How do we relate that? Okay, so first off, what we see is we have volume integrals, yeah? And what we remember maybe, hopefully, from second year calculus, and again, maybe I'll just pause here and just make it clear. What I'm going to do here is I'm deriving the weak form for you. I don't expect you to memorize this. I don't expect you to be able to do this out of your head or anything like this, but I do expect you to follow it so that you understand it and that you can see that this follows from logical arguments and standard mathematics. Yeah, that this is not something that is coming out of the sky or from heaven or anything. This is really something that is just following basic logical arguments in mathematics and just playing with the mathematics to get it into a certain form. This is what we are doing here. So this, please note, this is not something I'm going to test you on, but it is important that I do it. I'm not going to just tell you the weak form looks like this and then it's all faith-based. Engineering cannot be faith-based. It has to be logical-based. Okay, the bottom line. This is where I just want to make this point clear, that that you don't start stressing if you've forgotten a couple of things. But I just want to take you through. So this volume integral, we could maybe think, yes, but from second year maths, we knew about Gauss's divergence theorem that would allow us to relate volume integrals to area integrals. Yeah. So volume integrals we could relate to sort of surface integrals, but it allows us to bring in something about a normal. So this might be our cue, okay, that to sort of relate the stress tensor to a normal. This is a way to bring a normal in from mathematics. This is just a guess at this stage, and I want you to spot whether you can see where we would use this, for instance. So what I'm doing here is the Gauss divergence theorem of a vector. So the divergence of a vector integrated over the volume we can write as the vector dotted with the normal integrated over the area. Okay, and here it was the divergence of a stress tensor, a second order tensor, or divergence of a matrix that we had here. Here it's the divergence of a vector. Okay, so essentially you can see that this this dotted with this gradient operator dotted with a g of x will become a scalar, and what you'll see is this g of x dotted with the nx is also a scalar that will come out when I integrate it, then afterwards integrate over the area. What we had here was a vector dotted with a matrix that was resulted in a vector. Okay, so that just makes sure that we're on the same page. Cool. Bottom line. Now let's see what we can do with manipulating this. Okay, so first off, if I just look at divergence, okay, just divergence to a matrix vector product, I can apply divergence to a matrix vector product by saying it's the divergence of G times X plus the divergence of small g times big G. So what I just want to maybe make clear here is small g is a vector, big G is now a matrix. So this is now the divergence of the matrix transpose multiplied by g of x. If I do the divergence of this, it's equal to the divergence of g, yeah, times g of x. That's what that term is, plus the divergence of the small g, yeah, multiplied by the big G. That's essentially what we would get. Okay, so that's really, if I were to expand this divergence operator that was on this product, I would get something that was the divergence of the G multiplied with the G of X, and something that was the divergence of the small g multiplied by the big G of X. And this is what this term is all about. So this, I could take towards this side and say the divergence of G of X, big G, times small g is equal to g times the divergence of big G plus big G times the divergence of the small g. And this is what this term is. And this double dot here is a double contraction. I'm not going to talk about it now, but that's essentially something that I'll talk about in about 2 slides. Okay, so please take notes. And if I take then rearrange things, I can then say the g dot with the divergence of G of X is equal to the divergence of the product, matrix vector product, minus G double contraction with the divergence of the vector. That's essentially what we see here. Okay, so again, everything follows nice and logically from mathematics. I've just already written for you in this sort of form where we've isolated this term, because this is the term that maybe looks like this term. Yeah, this is why I'm isolating this term for you, is to say this G of X is sort of this vector V, sorry, vector W here. This divergence of a matrix is sort of the divergence of a matrix. Yeah, so this sort of form matches that form quite nicely. And so if I looked at that and say, okay, let's substitute this expression back here at the bottom and follow this sort of matching of small g is W, the divergence of the big G is sort of the divergence of the stress tensor, then I can say, oh, okay, so the divergence of this stress tensor transpose times W is sort of this term here, minus the stress tensor double contraction with the divergence of this W. integrated over the volume. That's what we have there. Yeah. So again, this is just one-to-one, just applying this divergence to a matrix vector product argument that I'm following here. Cool. We have not used this Gauss divergence theorem. I want you to spot where it's going to be applicable. So look at this form here. It's a divergence of a vector. So I want to ask you, just pause before I continue. Is anywhere here, am I applying the divergence of a vector alone? And if you ask yourself, what does this mean? This is a matrix times a vector, which is just a vector. So this is the divergence of a vector. So pay attention. Okay, so bottom line, this is essentially, where were we now? Let me make sure I'm following quickly my own. Okay, so this is essentially just copying this last line here towards this part here. That's what we had. Okay. And now what we're going to say is, fantastic. So this is this expression we can rewrite as these two terms. And now we can say, let's focus on this term specifically. And like I've already told you, alluded to the fact that this is the divergence of a vector. So if I look at the Gauss's divergence of a vector, which is this, it's the divergence of a vector, I can write it a volume integral as a surface integral with that vector dotted with a normal. So if I do that and I say this term here, I can rewrite as a surface integral, area integral of this divergence of whatever is inside that vector, inside there, that's that vector there, dotted with a normal. Minus this term that I had here before, and now if I just bring back the term that we've sort of forgotten about, this is the body forces, if I just add it in, this is the full-on expression. But now we've sort of incorporated something maybe about the normal and the stress tensor. Okay, so let's look in terms of how this is related to the stress tensor. So mathematical identity, we can go and say that the matrix vector product dotted with n, which is just a scalar in the end. This is a vector dotted with an n, which is just a scalar. We could rewrite in this form. Say it's sigma dotted with n, sigma multiplied with n dotted with w. These two things would be equivalent. Okay. How do I get to that essentially? Well, I could just maybe say, if we were to take this and we to take the transpose of all of that, I could write it maybe in a different format, and the order would sort of swap around. Okay, so we would start with the n, then the w, and the sigma. So that way won't work. But if you were to write it out, just quickly think about this quickly. What nice argument can I give you to make sure? I'm going to make it this way, maybe. Because I'm just taking this vector and I dotted with this normal, I could have dotted the normal on this side, doesn't matter, yeah? Which in the end it's just a scalar that I get out. So if I dot the n on this side, then I have n dot sigma transpose times w, yeah? And then I could say, well, instead of multiplying this first, I could have multiplied that first, because this is also essentially just a dot between sigma and w. That's a contraction that we have there. So if I'd just taken the dot on this side and say n dot with sigma, I could write as sigma multiplied by n. Doesn't matter, because the transpose, I could take this n multiplied by sigma transpose. If I take the transpose of that, I would end up with sigma n, and then I could just dot it with the w afterwards. And that's a maybe the quickest way I can explain to you why these two identities are exactly the same. So you can see this n I could have dotted to the front, and then I could have just taken the sort of a transpose of that expression. If I wanted to, or just think about the n dot with the sigma, do that first and then do the w afterwards. And then I have this, essentially this expression. Everything hunky-dory, nothing changed. Okay. So that's my mathematical identity. You can quickly see, because this is just a scalar equal to another scalar, and that these two things are then equivalent. And if I now look at the relationship of sigma n equals to t, this now allows me to say, if I can take this expression here, rewrite it as to this form, I know that this is just t, plug the t in, t dot w. And that's this expression that I have here. The area integral of t dot with w, area integral minus this term there that was there all along, plus the body forces equals to 0. Okay, and I can reorder the equations a little bit and say, let's take this towards this side and say it's this sigma double dot, this double contraction, which is an operator that I'll explain in a bit, but that's essentially just taking a matrix and double dotting it with sort of this this matrix, which gives you a scalar. Because if you think about this W partial W Wx, that is essentially a gradient operator, the gradient of W. But remember, we took the divergence of W multiplied by a matrix, and that's why this double contraction comes in. But I'll explain to you exactly what it is in a bit. Okay, so I can reorder things like this and say this is how things look. Double contraction of the stress tensor with this tensor here, which gives me a scalar. Dot product between two vectors, integrated over area. Dot product between two vectors, dotted over volume, integrated over the volume. So this is just a scalar equation that we have here. Okay. And this allows me now to write down what's called the weak form of the function approximation. Let me just see if it's a time on this video, if I want to stop it or whether I can continue. 15 minutes. So I'm going to stop this video now, and then I'll just continue in a sec on this video. Okay.